In this lecture, we are going to find number of electrons in the conduction band of intrinsic semiconductor. The band diagram is shown over here. Along the x-axis, there is interatomic distance, and on y-axis is energy axis. Here, this is the conduction band, and valence band. In the semiconductor, the Fermi energy level is in the middle of the energy gap. This is the energy gap, Eg, and in the middle of this line is Fermi energy level. In the conductor, this Fermi energy level lies in the conduction band. But in case of the semiconductor, this Fermi energy level is in the middle of the energy gap. One more important thing here, the lowest energy level in the conduction band is Ec, and the highest energy level in the valence band, we are going to call it Ev. That is, the topmost energy level is Ev, and bottom energy level in the conduction band is Ec. Now we have to find here number of electrons in the conduction band. You know that the product of density of states E, G of E, T, and the probability function, that is the Fermi-Dirac distribution function, this product gives us number of energy states occupied by electrons in conduction band. This gives number of energy states occupied by charge carriers. But you know that this density of states is nothing but energy states per unit volume in the range. This is energy states per unit volume in the range E and E plus D. And whether that states are occupied or not is given by Fermi function. And the product gives number of energy states occupied by the charge carriers. So what we have to find is number of electrons in the conduction band. So there can be many energy levels in the conduction band. The lowest energy level we are calling Ec, and above this Ec there can be many energy levels. We can say up to infinity energy levels are available. Out of these energy levels from Ec to infinity, which states are occupied is given by, if you integrate that with the integration limit from Ec to infinity, that is, let's see, the number of electrons is given by the symbol L in the conduction band. And as I told you, this G of E dE into F of E gives us number of energy states occupied by the charge carriers. In this case, charge carrier is electron. So number of states occupied by electrons is given by this product per unit volume in the energy range E to E and E plus dE. But in the conduction band, there are several energy levels, and that range is from Ec to infinity. To get the number of electrons In the conduction band, then we have to integrate this product with the limit from EC to infinity. Gives us number of electrons. Now to identify whether this density of states in the conduction band, instead of G of E, we will write here Gc of E. And in the conduction band, there are electrons. Charge carriers are electrons. So instead of saying F of E, we will say Fe of E. That E denotes, that small e denotes electrons, and this C denotes the conduction band. So let me write here this Gc of E is nothing but density of states in the conduction band. Density of states in conduction band. And this Fe of E is Fermi-Dirac distribution function of electrons in conduction band. This is Fermi-Dirac distribution function of electrons in conduction band. Or you can simply say Fermi function of electrons in the conduction band. So let me write the value of this Gc of E. This Gc of E is density of states, and this density of states is equals to 4 pi by h cube 2 me star raised to 3 by 2, and here instead of E there is a E minus EC, as EC is our lowest energy level. So E minus EC, any energy level above EC. So EC is the reference energy level in the conduction band. In this equation, as you know that this H is Planck's constant, me star is effective mass of electrons. Effective mass of electron. And with the E minus EC is any energy level above EC. EC is the reference energy level in the conduction band. In conduction band. So this is, let's say, let's name it. This is our equation 1. The Gc of E is our equation 2. And then the probability function, Fe of E. This Fe of E is equals to 1 upon 1 plus e raised to E minus Ef by kT, Fermi-Dirac distribution function. But in this case, as E minus Ef is very large compared to thermal energy kT, as you can see in this diagram, this is the Fermi energy level Ef, which is in the middle of the energy gap, and we are considering any energy level in the conduction band. So this energy gap, this energy difference, let's say this is E. So this E minus Ef is very large compared to kT. And therefore, we can neglect this one. This quantity would be very large. And so we can neglect this one, and let's take this term above this. So let's write this as Fe of E is equals to e raised to minus of E minus EF upon KT. Let us simplify this. This is nothing but e raised to minus of E. What I am going to do here is subtract EC and add EC. EC minus EC plus EC minus EF divided by KT. I just did a little arrangement by adding and subtracting EC. This equation further we can rewrite as e raised to minus of EC minus EF, this one, by KT into e raised to this one, e raised to minus of E minus EC upon KT. We have just rearranged this equation. So instead of writing e raised to minus of E minus EF by KT, we can write this term. And let's say this is equation 2. Not 2, this is 3. This is our equation 2 and this is equation 1. So we have three equations, 1, 2 and 3. So let's substitute equation 3 and 2 in equation 1. So equation 1 is nothing but the number of electrons n, which is equals to integration from EC to infinity. The first one is GC of E and then Fe of E. GC of E is given by this and Fe of E is given by equation 3. So GC of E is 4 pi upon h cube 2 me star raised to 3 by 2 into bracket E minus EC raised to half into equation 3 is Fe of E, that is nothing but E raised to minus of EC minus EF by KT into E raised to minus of E minus EC by KT into dE. So we have just substituted equation 3 and 2 in equation 1. Now let's see this equation which I wrote just now. In this equation, this term is constant. Similarly, this term is also constant. EC minus EF is constant. Why EC minus EF by KT constant? See, EC is the lowest energy level and EF is the Fermi energy level in between energy gap. So this difference EC minus EF is constant, and so E raised to minus of EC minus EF is constant. So in this equation, we will take this constant term outside the integration and let us rewrite it. So number of electrons n is equals to 4 pi by h cube 2me star raised to 3 by 2 into e raised to minus of ec minus ef upon kt. So this is constant. Then integration from ec to infinity. This term is remain. So e minus ec raised to half, and then this term e raised to minus of e minus ec by kt into dE. Now to solve the integration, we are going to use a standard formula. And the standard formula is standard formula is integration from 0 to infinity x raised to half into e raised to minus ax dx, and this is equals to root pi upon 2a root a. So this is the standard solution for this integration, the standard formula. So in this case, if you compare this with this, in this case the integration is from 0 to infinity. In our case, there is the integration from EC to infinity. But EC is our reference energy level. So the same formula we can apply. In this case, X is E minus AC, E minus EC, and this A is 1 by KT. A in this case, this A is nothing but 1 by KT. And so the solution is root pi upon 2 into A. So this is 2 into 1 by KT into root 1 by KT. Simplify it, and what you get is root pi by 2 into KT raised to 3 by 2. So this is the solution of the integration. So let us substitute this solution in this equation and rewrite it. N equals to, the constant terms are 4 pi by h cube, 2 me star raised to 3 by 2 into e raised to minus of ec minus ef by kt. These are these terms. They are as it is. And the solution of this integration is this into root pi upon 2 into kt raised to 3 by 2. So this is the solution. Number of electrons in the conduction band. Let us simplify it. To simplify it, I will take this term to this side, and then 2 into 2 pi me star k t upon h square raised to 3 by 2. Then into e raised to minus of ec minus ef upon kt as it is. These terms are constant, which are in the bracket. The bracket terms are constant. So number of electrons, let us write this is constant, and that is equals to Nc. So Nc into e raised to minus of Ec minus Ef upon Kt, where Nc is equals to 2 into 2 pi me star kT upon h square raised to 3 by 2. That is Nc. It's a constant. And this Nc is nothing but effective density of states in conduction band. And therefore, number of electrons in the conduction band is given by Nc e raised to minus of Ec minus Ef upon kT. By this formula, we can find number of electrons in the conduction band.